In today's video, we'll be discussing the monumental figure of Gottlob Frege. Frege was a German mathematician living in the 19th century. He made profound contributions to the axiomatic method and the foundations of mathematics, which have had a lasting impact on the field. He was the pioneering mind behind what we know today as predicate logic, a fundamental tool that ensures the rigor of mathematical proofs as we understand them today, underscoring the necessity of his invention. It's important to note that Frege's life work faced a significant setback when he encountered challenges regarding the implications of using a too loose definition of mathematical concepts. In some of my last episodes on the axiomatic method, I discussed Leibniz's idea of creating a characteristica universalis, a general language that would enable us to express the truth and only the truth about the real world. While Leibniz never made his idea real, George Boole invented almost 200 years later a symbolic system he called the laws of thought, for which I produced another video. Feel free to check out both videos as an introduction to this one. Despite Boole's breakthrough, Boole's language was not expressive enough to formulate mathematical proofs. 20 years after George Boole's work, Frege published his 88-short booklet Begriffsschrift, the language of thought. Frege enriched the expressiveness of his language to the extent that Leibniz's idea suddenly seemed accessible and feasible. In his foreword, Frege laid out the purpose of his booklet. He directly referred to Leibniz's Characteristica Universalis and considered his Begriffsschrift a continuation of Leibniz and Boole's ambitions to create a universal language of mathematics. Frege acknowledged that Leibniz failed to create such a language, but this didn't mean we shouldn't try inventing one. Frege promised himself that his language would find a successful application, especially when formulating, quote, concise mathematical proofs, unquote. As I said before, Frege's notation is richer and therefore more expressive than Boole's approach. As it comes to variables, in Boole's notation, variables always denote statements that are a priori true or false. Only two values are allowed. In mathematics, we call such statements propositions. In Frege's language, variables denote any concepts and ideas. Frege differentiates between non-accessible or accessible concepts. An example of a non-accessible concept would be the concept of a house. While the sentence there is a house is an accessible concept. In other words, an accessible concept has the potential of being able to be proved. A non-accessible concept cannot be proved or disproved. It is just a single idea of an object like a house. While accessible concepts have the potential of being true or false, or to be proven or disproven. In that sense, Frege's accessible concepts are like Boole's propositions. However, they are not true or false a priori. They only become true or false if we can prove them. So, they are true or false a posteriori. We call such constructs predicates. As it comes to logical operations, Boole introduced separate symbols for a logical OR, a logical AND, and a logical NOT. At the same time, Frege only used symbols for a logical NOT and a logical implication. Both systems are equivalent because as it turns out, we can transform these logical operations and express the same using only the respective set of symbols. Both notations use the equality relation. Also, both systems allowed parentheses to disambiguate expressions. However, Frege invented a completely new functional notation. In Frege's terminology, a function was different from what we typically understand it to be in the mathematical sense. Frege's functions were a special type of variables to abbreviate complex parenthesized expressions involving other variables. He called the functions arguments. Today we call Frege's functions predicates because they are statements stating properties of variables in a linguistic sense. What is important to know is that Frege allowed his functions or predicates to be both determinate and indeterminate. This fact will become important later in this video because indeterminate functions became the logical trap that finally led to the collapse of Frege's lifework. Finally, Frege introduced a symbol to express that an accessible function that depends on some argument is a fact regardless of the argument. This symbol, known today as the for all quantor, is a fundamental concept in logic. Equally important is the exists quantor, which Frege could derive using the symbol for his for all quantor combined with his symbol for the logical NOT. In summary, Frege's notation was much more expressible than Boole's. In his 88-page booklet, Frege introduced nothing less than what we call today the predicate logic of first, second, or, in general, a higher order predicate logic, also denoted by PL1, PL2, etc. In contrast, Boole only introduced propositional logic, which we call today zero-order predicate logic, also denoted by PL0. A PL0 is where we have no predicates. In PL1, we have first-order predicates. It means predicates whose arguments are objects. In Frege's terminology, those are the non-accessible concepts, like a house. In PL2, we allow predicates with arguments being first-order predicates. For instance, there is a house. Such functions then become second-order predicates. This hierarchy goes on in PL3, PL4, and any higher order logic, that is, n-order predicates have arguments being n-1 order predicates. But usually, PL2 is already powerful enough to express modern mathematics. Therefore, as you see, Frege came to Leibniz's dream of creating an artificial language capable of expressing the truth about the real world already very close. Let us look at some examples to give you an impression of Frege's notation. Frege proposed a two-dimensional notation that was so innovative that it was never really accepted. Still, many of Frege's innovative ideas survived and became part of mainstream mathematics, as we will see later. In this table, you see to the left Frege's original notation. The middle column contains a description of what the notation means, and the column to the right contains how we would express the same in modern mathematical notation. Let us look at how Frege denoted that concept A can be accessible. His vertical line denoted that we have some given mathematical content. The horizontal line means that the concept A can be assessed from this content. Recall that Frege's variables, like here A, could be either accessible or not. By putting the lines before A, Frege expressed that we have a variable denoting a concept that can be assessed. Today we would say that A is not an object, like for instance a house or a natural number. Instead, it is a predicate that can be proved. Indeed, even today's notation is very similar to Frege's invention. In logic, we use the vertical and horizontal bar, called turnstile, as the sign that we can logically derive the theorem A. Frege's next symbol was to indicate the equality of two mathematical concepts. It's crucial to understand that there is a subtle difference between equality in mathematics and how Frege uses it. By placing the turnstile before the parenthesis with the equality A equals B, Frege isn't stating that A and B are equal. Instead, he is expressing that the equality of the two variables can be proven, a key concept in his mathematical logic. It's crucial to remember the subtle difference between an expression, like A equals B, and the same expression with a turnstile preceding it. This turnstile, a key element in Frege's notation, signifies that we can prove that A equals B. Given that turnstiles are a recurring element in almost every one of Frege's expressions, I won't need to reiterate this. Frege's next two symbols denoted the logical negation and the logical implication of variables. Interestingly, the modern sign of negation is still similar to Frege's original. The logical negation and the logical implication are complete in the sense that we can express other logical operands, including the logical OR and the logical AND, without having to invent new symbols for them. This comes at the cost of the notation becoming more cumbersome. Let us look at how Frege expressed the logical OR in his notation to demonstrate his notation becoming cumbersome. The expression to the left reads, not B implies A. To see that this is equivalent with the disjunction B or A, we have to go through two steps in our mind. You have to know that in logic, an implication P implies Q is equivalent to the disjunction not P or Q. Applying this to Frege's notation, we get not B implies A equals not B or A. At this step, we have to know that a duplicate negation cancels out in logic. Applying this to second rule, we have finally arrived at the disjunction B or A. Note that Frege renounced to invent an additional symbol for the logical OR, also called as a disjunction. Note how Frege's notation became increasingly cumbersome while remaining to get along with fewer symbols at hand. Similarly, Frege had no separate symbol for the logical AND, called a conjunction. Instead, he used a combination of negation and implication. On the left side, it reads B implies not A, which is negated as a whole. In modern notation, we have to put parentheses after this first negation. By applying the first formula, we can translate it into the negated not B or not A. At this step, we need one of the De Morgan laws, which tells us how to simplify the negation of a parenthesized disjunction. Applying the De Morgan law and also the previous double negation law, our expression becomes the conjunction B and A. Before we get to Frege's notation of functions, let me first explain what Frege actually meant by functions. As I said before, Frege presents his Begriffsschrift as a continuation of Leibniz's idea to create a lingua characteristica, a symbolic language. We can find this linguistic concept of subject-predicate-object structure in natural languages. In Frege's example, the judgment hydrogen is lighter than carbon dioxide follows this structure. We have a subject, hydrogen, a predicate is lighter than, and an object, carbon dioxide. Frege says that when trying to express his sentence in his Begriffsschrift, he decided to replace, quote, the concepts of subject and predicate by argument and function, respectively, unquote. And that is, he believes, quote, will stand the test of time, unquote. He was right. To understand better Frege's ingenious idea, he regards the sentence's content as a function of one or more arguments. In this particular example, the subject and the object are replaceable. For instance, we might say, oxygen is lighter than sulfur dioxide, while the predicate is lighter than remains. On the other hand, we might replace the predicate by saying hydrogen is heavier than carbon dioxide. Frege noticed this is similar to how mathematicians treat functions and their arguments. By replacing hydrogen and carbon dioxide with some variables, we can treat those variables as arguments of some function, which in our case is the predicate is lighter than. So, in summary, our original judgment can be expressed as a functional term like we know it from mathematics. Frege allows his functions to be indeterminate, that is, being just some replaceable symbols. For Frege, indeterminate functions were replaceable because he was convinced that each specific instance of a replacement would always symbolize something meaningful, so that we either can prove or disprove it. For Frege, an indeterminate function becomes a judgment once we can prove or disprove it. And disproving something means proving the opposite. Unfortunately and sadly, Frege was wrong at this point. As we will see soon in this video, allowing his functions to be indeterminate or replaceable by any predicate you like was wrong. This assumption was the root cause of why he, after many years, considered his life work as failed. But we will come back to that point later in this video. Returning to our notation overview, let us hold on to the fact that Frege formalized predicates with functional symbols, which stood the test of time. This is exactly how we express predicates and functional terms in today's predicate logic. It would lead too far to explain the difference between functional terms and predicates at this point. If you like, check out my video on the types of definitions in mathematics. By the way, note how Frege's formalization all of this of a sudden allows us to create higher order logic. By simply allowing the arguments of a predicate to be predicates themselves, we can easily and precisely construct higher order logics with Frege's notation. When it comes to functions, Frege invented a way to generalize the arguments of a function. By introducing this symbol here, he introduced what we call today the for all quantum in logic. The for all quantum means that whatever we may take for the argument, of course within the limits of the order of predicate logic in which we operate, the function is a provable fact. Finally, using two negations combined with the for all quanta symbol, Frege expressed what we call today there exists quanta in logic. As in previous cases, deciphering Frege's notation is a task that requires a series of steps. The expression to the left states, not for all A, lambda A is not a fact. There is a rule of how to negate the for all quanta. Since not for all A something holds, it means that there is an A for which this something does hold. Applying this rule to our case, this something equals not lambda A, which we have to negate again. In total, we get the expression there exists an A for which not lambda A holds. For this, again, we need our double negation rule, simplifying our expression finally into there exists an A with lambda A. So, let's summarize what we have seen so far. In his Begriffsschrift, Frege's approach marked a radical departure from the prevailing use of natural language in expressing mathematical theorems and proofs, instead favoring the use of symbols. His invention of a symbolic language liberated mathematical proofs from the constraints of symbols semantics, shifting the focus to the application of syntactical rules. From this alone, I would say Frege's Begriffsschrift is a profound leap forward for mathematics. With his systematic way of classifying symbols into objects, predicates, and functions, Frege's notation successfully addressed the ambiguity of language, either natural or symbolic, when it comes to formulating mathematical theorems, definitions, and proofs. While Boole's notation could only express logical relations between 0 or 1 valued variables, Frege proposed an extended notation involving functions with arguments that could deal with different universes of discourse. This invention and his quantifiers were a big leap to improve the expressiveness of the symbolic language, taking formal logic from what we call today propositional to predicate logic. But Frege's contribution to maths and logic continues beyond there. Guided by his unwavering faith in the power of his new language, Frege embarked on a monumental quest to decipher the mystery of natural numbers using this very language, a task of immense significance in the world of mathematics. You might think, why on earth would mathematicians ask themselves what numbers are? Isn't it something that is basic school stuff everybody should already know? Well, let me take you on a short journey on which I promise to amaze you, so if you think you know what numbers are, you will doubt it afterwards. When you think about mathematics, the first thing that comes to the mind of most of us is whole positive numbers. We call these numbers natural. We can use natural numbers to define whole numbers. Those include both positive and negative whole numbers. There are some rigorous ways to do this, but I do not focus on the technical details here. It is only important to notice here that natural numbers can be chosen to be the foundation for whole numbers. Again, in some technical and rigorous ways, we can construct rational numbers that allow ratios between whole numbers. Whole numbers are the foundation for rational numbers, but are built on natural numbers. Already, the ancient Greeks knew that there are some numbers like the square of root of 2, for example. A ratio of two whole numbers cannot represent that. We call those numbers real. Again, we can base the definition of real numbers on rational numbers in some rigorous sense, but I don't want to discuss these details here. It turns out that many mathematical problems, but also practical engineering problems and problems in physics, cannot be solved using real numbers alone. We have to further extend the available number system to so-called complex numbers that we can also define rigorously using real numbers as a foundation. Note that in each step we extend the realm of numbers to a bigger generalization. It is a generalization in each step because the calculation rules remain the same, example doing addition or multiplication. Because we generalized our number systems in each step, we can now look at every natural number as a specific instance of a whole number. Every whole number can be seen as a specific instance of a rational number, every rational number can be seen as a specific instance of a real number, and every real number can be seen as a specific instance of a complex number. Because with the higher number systems we gained more general number systems, it seems that we can, for now, explain natural numbers simply by saying that they are some specific whole numbers. We might think we can now simplify everything by eliminating natural numbers from our pyramid of number systems, since they are only a special case of whole numbers. Similarly, we could eliminate whole numbers, since they can be regarded as special cases of rational numbers. We can somehow explain whole numbers if we know what rational numbers are by saying they are special cases of our more general rational numbers. By repeating this process, we can eliminate all number systems except the top one we invented, the complex numbers. Because we can always say that any preceding number system is just a special case of it. If it seems to you like a sleight of hand trick, you are right. It looks like we could somehow eliminate the more foundational number systems because we have retrieved more general ones. It's crucial to note that to have come so far, we needed the preceding number systems as a foundation for the succeeding ones, underscoring their significant role in explaining what the latter are. So forget about the sleight of hand trick. Of course, we cannot eliminate foundational number systems without which all derived number systems would collapse like a house of cards. We cannot explain what more foundational number systems are using number systems we derived from them, even though we managed to create generalizations of the more foundational number systems in each step. I hope I have intrigued you. This was my purpose. The seeming paradox arises from the distinct cognitive processes of generalization and foundation. Regardless of our cognitive understanding of numbers, it's crucial to remember that natural numbers are the fundamental building blocks of all other number systems and huge parts of mathematics, physics, and engineering. Therefore, we have to make sure that all we do in mathematics, physics, and engineering does not collapse like a house of cards, simply because we made somewhere a huge mistake. This mistake could be a hidden, undiscovered contradiction in our logical reasoning. Since we cannot explain natural numbers using more general number systems, and since natural numbers lack a separate foundation, what natural numbers are remains a mystery, with a potential of hidden contradictions. This is where Frege comes into play. Frege was convinced that his Begriffsschrift should finally become the tool with which he could lay out the foundations of mathematics, but by logically justifying natural numbers. All he still had to do was to provide logical axioms for his symbolic language Begriffsschrift, and after he managed to do it, to express what natural numbers are in Begriffsschrift. This concept, known as Logicism, was a cornerstone of Frege's work, and he was one of its most significant pioneers in the history of mathematics. Therefore, throughout his life, Frege followed the following program. First, develop a capable formal language. Begriffsschrift. Second, establish logical axioms for this formal language. Third, express what natural numbers are in this formal language. In particular, express what is a mathematical sequence, what is 0, what is 1, and what is the successor of n given a natural number n. In fact, in his 88-page booklet Begriffsschrift, Frege was on the best track to accomplish his program. A half of his project has already been implemented, although after the publication of Begriffsschrift, the work remained mostly unnoticed in the mathematical community. But Frege stayed on track and was not discouraged by the lack of notice in his readership. Well, this video series is about the axiomatic method. Therefore, I won't delve into the details of how Frege defined what a mathematical sequence is. However, I want to show you Frege's axioms. Frege never called them axioms, but described them as rules that, quote, cannot be expressed in the ideography because they form its basis, unquote. Frege introduced 9 axioms, and we could classify them based on their syntax into purely propositional and purely predicative axioms. The latter using Frege's innovative extensions of his language, like functions, quantors, and the equality relation. These axioms are the foundation of all other rules Frege was going to derive using his Begriffsschrift, including the foundation of natural numbers. Frege was convinced that these axioms will solidify arithmetics once and for all, because they are indisputable in a transparent, explicit sense. Take the axioms at paragraph 54 of Frege's Begriffsschrift as an example. No matter what the variable c denotes, it is a fact that c equals itself. Cognitively, there are 2 instances of the same variable, but it does not depend on psychology. Today we know automated algorithms using computers to identify c as the same variable in both instances. And this approach has nothing to do with subjective cognition and perception. The mechanics behind a formal language like Frege's Begriffsschrift is a main feature for objectivity, solidifying his axioms. Nevertheless, we could still argue that even the logical calculus process can be objective. There still might be the case that once we combine Frege's axioms together, that will lead to some contradictions, making Frege's collection of axioms inconsistent. Moreover, the collection might be incomplete in the sense that not all true statements about natural numbers could be proved using those axioms alone. Or Frege's collection of axioms is redundant because we could eliminate some of its axioms since they can logically be derived from other axioms in the same collection. Frege never addressed in the issue of his axioms consistency, completeness, independence, or other meta-mathematical questions. What meta-mathematics is and what these terms mean for the axiomatic method will become crucial in future videos from this series. Stay tuned. By the way, if you haven't already, subscribe to my channel and activate the bell so as not to miss the continuation of this series. Returning to Frege's monumental quest to establish a logical foundation for natural numbers, 5 years later he reached a pivotal moment for his Grundlagen der Arithmetik, the basics of arithmetics. This book is a philosophical treatise that critically examines all previous attempts to elucidate natural numbers, be it through cognition, physics, or linguistics. In his treatise, Frege dismantles the inadequacies and circularity of existing approaches, paving the way for his groundbreaking logical method. He presents a prose description of his innovative approach, defining the numbers 0, 1, and the successor of any given number, confidently asserting that this could be easily expressed in his Begriffsschrift. Looking at the timeline, Frege published his Begriffsschrift 2 years after Cantor's first publication, in which he introduced set theory for the first time. While Frege was aware of Cantor's work in set theory, he distanced himself from it in the Grundlagen of Arithmetic. Yet, in modern terms, his approach could be likened to set theory, akin to Cantor's cardinal numbers. His approach to numbers, however, was not sets but logical predicates. Frege felt greatly discouraged by the cool reception, or rather the lack of reception, of his work, as he noticed himself in the introduction. For instance, the German mathematician Richard Dedekind published 1888 his paper Was sind und was sollen die Zahlen? What are numbers and what should they be? Without even taking notice of Frege's Begriffsschrift and the Grundlagen of Arithmetic. 1 year later, the Italian mathematician Giuseppe Peano published his Arithmetices Principia, a work that contained what we now know as the Peano axioms of arithmetics. Peano was completely unaware of Frege's work. He wrote it in his foreword, quote, "Questions that pertain to the foundation of mathematics, although treated by many in recent years, still need a satisfactory solution. The difficulty has its main source in the ambiguity of language. My goal has been to undertake this examination, and in this paper I am presenting the results of my study and some applications to arithmetic. I have denoted by signs all ideas that occur in the principles of arithmetic, so that every proposition is stated only using these signs." Unquote. This must have been devastating for Frege, who addressed the very issue already 10 years before. Peano's work was significant as he managed to create a formal language that was much more readable than Frege's Begriffsschrift. Furthermore, Peano's and Dedekind's work combined revealed that every structure that fulfills the Peano axioms is isomorphic to the natural numbers. In other words, all structures fulfilling the Peano axioms are natural numbers. They differ only by the symbols, not by the meaning of these symbols. This was a huge breakthrough as regards to explain what natural numbers are. Despite the discouragement he felt, Frege's perseverance was unwavering. He continued to work on the Logicism approach, and in 1893 he published the first volume of his monumental work Grundgesetze der Arithmetik, Basic Laws of Arithmetics. This work finally formulated all his ideas from Grundlagen der Arithmetik in his symbolic language Begriffsschrift, which means differently than Peano and based on logical axioms rather than Peano's axioms. However, the mathematical community still needed to take due notice of Frege's work. For instance, in 1899, another German mathematician, David Hilbert, published a groundbreaking work in which he provided a foundation of geometry. It was an alternative to Euclid's over 2000 years old original. By the way, there is a previous video from this series on Euclid's work. Check this out. Hilbert must have known Frege's and Peano's work, but refused to use their respective notations. Moreover, similar to Frege and unlike Euclid over 2000 years ago, he defined geometrical objects like lines, points and planes, not relying on visual insights and their essence, but by putting them into predicative relations. In Hilbert's approach, lines, points and planes became replaceable, meaningless symbols. What gave meaning to these symbols were the predicative relations between them. And like Frege, Hilbert defined axioms predicatively and derived all theorems from these axioms using strict logical reasoning. Again, this was almost a copycat to what Frege did for arithmetics 6 years before in his Grundgesetze der Arithmetik, but nobody was willing to notice it. Despite all these setbacks and the lack of reception of his work, Frege was ready to publish his draft second volume of Grundgesetze der Arithmetik. But all of a sudden, Frege received 1902 a letter from the British mathematician and logician Bertrand Russell. Russell was very respectful to Frege's work. He wrote his letter in German and was very friendly and courteous. In his letter, Russell mentioned Frege's publications and praised them. Unfortunately, this was only the introduction of the letter. Referring to page 17 in Frege's Begriffsschrift, Russell wrote, quote, "I only encountered a difficulty at one point. You claim, page 17, that the function can also form the indeterminate element. I believed this before, but now this view seems doubtful because of the following contradiction. Let W be the predicate, a predicate which cannot be predicated by itself. Can W be predicated by itself? The opposite follows from every answer." Unquote. This was a bombshell to Frege. Only 5 days later, on June 21, 1992, Frege answered the letter. He wrote, "Your discovery of the contradiction has surprised me greatly, and I might almost say dismayed me, because it undermines the foundation on which I thought arithmetic would be built." Unquote. Frege also immediately identifies a bunch of logical flaws in his newly published Grundgesetze der Arithmetik. He writes, quote, "It therefore appears that the transformation of the generalization of equality into equality of value progression, section 9 of my basic laws, is not always permissible, that my law 5, section 20, page 36, is wrong, and that my explanations in section 31 are not sufficient to ensure a meaning for my combinations of symbols in all cases," unquote. Russell's formulation of his antinomy and Frege's reaction to it are complicated and not easy to understand today because of the antiquated terminology and notation as they appear to us today. But it is crucial to delve into the true significance of Russell's antinomy in Frege's work. This will give us a clearer perspective on the challenges Frege suddenly faced. Before we get into why precisely Russell's antinomy destroyed Frege's lifework, let us start with a clarification Frege himself wants to achieve in his answer letter to Russell. He writes later in his letter, quote, "Incidentally, the expression 'a predicate is predicated by itself' does not seem to me to be precise. A predicate is usually a first-order function that requires an object as an argument and thus cannot have itself as an argument subject. I would therefore prefer to say a concept is predicated by its own value progression. If the function phi of xi is a concept, then I designate its value progression, or the associated class, by epsilon prime phi of epsilon. The justification for this has now become doubtful to me. In phi of epsilon prime phi of e, we then have the predication of the concept phi by its value progression." Frege noticed that Russell is suggesting the paradox that predicating the concept phi by its value progression is logically equivalent to its negated version. Why had Russell's paradox greatly impacted Frege's lifework? Well, it's because Frege formulated a series of basic laws to justify arithmetic, which he added to the axioms of the Begriffsschrift, one of which was his basic law 5 that had been referenced throughout his work multiple times. The basic law 5 states that a value progression equality can always be converted into a generality of equality and vice versa. When Frege wrote this basic law, little did he know that he had permanently damaged his logical foundation at a crucial point. Using a modern notation and set theory, the law 5 can be reformulated as follows. If the graphs of two functions are equal, then the function values are equal at every point, and vice versa. This sounds plausible, or even indisputable. The point is that Frege insisted it was always the case. Russell pointed out a counterexample, a predicate for which it is not the case. In fact, by allowing predicates that are degenerated in Russell's sense, the whole law becomes meaningless. One year after Russell's devastating letter to Frege, he published his second volume of Grundgesetze der Arithmetik, knowing full well that his life work lay in ruins. From today's perspective, we deeply value Frege's work. He was a pioneer in the history of mathematics, creating a formal, unambiguous language that could express modern mathematics. I want to conclude this timeline with a quote. The German author Dirk Hoffmann says, quote, "All this recognition comes too late for Frege. He was worn down by the long struggle to gain acceptance for his work. The final discovery of paradoxes in 1902 was a devastating blow from which he would never recover. He saw his life work as a failure and published since then only a few insignificant works. He passed away as a lonely and embittered man on July 26 in 1925 at the age of 76." Unquote. Regarding the axiomatic method, Frege was not the only tragic figure. We will see in a later video that David Hilbert would suffer a similar fiasco in his life work as Frege. But this is another story. Before I tell you the story of David Hilbert, in the next video, we will first examine the different approaches mathematicians tried to rescue the foundation of arithmetics proposed by Frege and Peano. These approaches range from the logicists' approach of Russell, over constructivism approaches of Brouwer, over formalism approaches by Hilbert, to the further development of set theory by Zermelo and Fraenkel. I hope you found this video informative and engaging. Stay tuned for the next part of our journey into the history of the axiomatic method. Bye for now.